Hey everybody, I hope you've had a good weekend. Hope everybody's staying safe. I miss all you guys. So last class, we did section 9.1, where we remembered or reintroduced some special things about functions. We also worked on composite functions, or composing functions, sticking a function inside a function. That'll be a little bit useful in today's lesson as well. So today, we're going to talk about inverse functions. Sorry, did not mean to yawn. I'm kind of sleepy here. Don't know what time you'll watch this, but it's late at night when I'm doing this. So, at least late for me. Inverse functions. Okay, so the first question we need to kind of start with is, what is an inverse function? Okay. Well, an inverse function is when we take a function and all we do is we swap its inputs with its outputs. Or you might say its domain with its range. So these things trade places. So remember, what's the domain? The inputs, remember, those are the x values. Whoops, let me get a pin here. So we're swapping the x values with the y values. Whoops, and I'm trying to make up a new word. With the y values. I don't know about you, but that seems pretty simple, at least on the surface, and it actually really is. Okay, so for example, let's just start with an example right off the bat. Remember, we can represent a function with a set of ordered pairs. Can you write me the inverse? And you say, oh, all we have to do is switch the x and the y values. So 1 and 4 relate. So if I wanted to write the inverse, instead of 1 and 4, remember this is an x and a y value. If I switch them, 4, 1. And 2 and 7, I could switch them and get 7 and 2. 8 and 2, I could switch them and get 2 and 8. And I just go about switching all of the x's and the y values. 0, 9 would become 9, 0. And there I have written the inverse of this function here. So I've written the inverse function. That's really simple then, right? Just switching the x's and y's. So the next question is, okay, we could do that with points. Can I do this on graphs? And the answer is yeah, I could do the same thing on graphs. So let's look at some examples. So here's a graph. Now the only thing that people struggle with is you actually got to pick some points that are on the graph to switch the x's and y's. Okay? I gave you some points here. I put some dots on some points to use. You can pick any points you want, but let's see. I got -1, -1. So I might actually write them out to the side. -1, -1. What's another point I got? 0, 1. 0, 1. 1, 3. 1, 3. And I picked 4 points just to have enough. 2, 5. So if you were to switch those, you would get the inverse, right? Let's do it in purple. So switching -1 to -1 is going to be -1, -1. I know, not exciting because those are the same x and y value. But anyways, switch 0, 1, 1 and 3, and 2 and 5. And let's plot these points and draw the line through them. So -1, -1, I got that point. 1, 0 is going to be there. 3, 1. And 5, 2, and draw the line through it. Okay, so I'll go ahead and tell you this. The shape will be about the same. It'll just be like reflected over this diagonal line here. So notice it looks like a mirror image across that diagonal dotted line that I drew. Okay, but it's pretty easy to draw an inverse if you can just pick some points, swap the x's and y's, and then trace your points. So that's really easy. So here's another example. Let's do this one. I gave 5 points. Let's pick these 5 points. Let's switch them and then draw the inverse. Okay, so what are the points? Let's see if we can, well, no, we might as well list them out. -10, -2, I believe. -10, -2. Oh, I already switched that one. That's actually, man, I am tired. Let's see. -2, -10 is what that point is. The next point's -1, -3, 0, -2, 1, negative 1, and 2, 6. So let's swap these. We'll do it in red. And if I swap these points, so this seems really easy as long as you're not as crazy as me and miswrite points sometimes. All we're doing is swapping x's and y values, right? And it is that easy. We're going to dive a little bit deeper. Let's see. Negative 10, it won't fit on the graph. Negative 10, negative 2 is about out there, right? Negative 3, negative 1, negative 2, 0, negative 1, 1, and 6, 2. So about like that. See if I attempt to draw this curvy graph perfectly. That's good enough. Y'all got to give me credit. That's pretty, right? And once again, notice that it looks like a mirror image reflected across that diagonal. Awesome. So everybody feels like they could find the inverse function given points. They could find the inverse function of a graph. Now, I will not put these points on there if I give you a problem. You have to pick some points, but just pick points that are exact numbers, okay? All right, so let's move on. If I could do a graph and I could do points, can I find the inverse function with the equation? The answer is yeah. So how am I going to switch the x's and y's? What is that going to look like? And actually, it's not too hard. I'm actually going to just show you some examples, and we'll do it that way. Let me cover up the next example. So instead of function notation, let's actually do it as x's and y's. So you'll see how this looks. So I'm going to throw out the function notation for a second. I have the y there, okay? I just replaced it with the y. So remember, all we're doing is switching x's and y's. So can't I just say, well, switch the x's and y's? X over here, y right there. Ah, that's nice. Now, this is not in function notation, though. We'd like to get it in function notation. To get it in function notation, you have to solve for y and then write some fancy notation. Okay? So how would I solve for y here? I just need to subtract 3 from both sides. So what would this be? X minus 3 is equal to y. Now, I would like to write this y in a fancy way. I'm going to write it over here. Instead of y, I'd like to write it in function notation. Now, I don't want to call it f of x because this is a different function than that one, right? So what we do is we say, okay, this is the inverse. Let's just call it f to the negative 1 power of x. This is not literally the negative 1 power. This just means it's the inverse. F negative 1 of x is x minus 3. So this and this, these two functions are inverses. So literally, all you do is swap the x and y, solve for the y, and then use the fancy notation. Okay, let's do a few more examples just to get cozy with this idea. So here's another one. Can I come up with the inverse? Well, once again, let's get rid of the fancy notation for a second. That's what this really means, right? Y equals 3x minus 5. Swap them. X equals 3y minus 5. Now, let's solve for y. I gotta add 5 over. So x plus 5 equals 3y. Is y by itself yet? No. What's with it? It's a 3. How do I get rid of this 3? I divide both sides by 3. Now divide the whole thing by 3, but whole side. So what do I get? Let's carry it over here. I have y all by itself. It's equal to x plus 5 over 3. Can I write it with fancy notation? Yeah. F inverse, so don't forget the negative 1 right there, is x plus 5 over 3. So hopefully you're thinking this is pretty easy. Notice that to write the inverse function, I'm using inverse operations because I'm solving, right? One more example of this. How about this one? Well, once again, let's drop the fancy function notation. And here we are, and you say, switch the x and the y. Yeah. All right, beautiful. And then you say, okay, well, how do I solve for y this one? Well, I got to get rid of this third power. Remember, to get rid of a power, I do the same root. So I'm going to third root both sides. That's from our last chapter, right? So the root and the power cancel, and I'm left with 5 plus 5. That's a y. Y plus 2 is equal to the third root of x. Is y by itself yet? No, I need to subtract 2. So third root of x minus 2 equals y. So here's what I'm looking at. Y equals the third root of x minus 2. Can you write it with fancy notation? Yeah. F inverse of x is equal to cube root of x minus 2. So there, we wrote the inverse function. So does that seem that hard? No, not really. So we could do points, we could do graphs, we could do equations. We can find the inverses of these equations. So that's really awesome. So now we've confined these inverses. Let's talk a little bit about some of the special details or special relationships with these things. So remember, Algebra 1, you're studying relations between x's and y's. And we learned there's a special one called a function. And I will go ahead and tell you, it's a little bit lame because there's a lot of really neat things you get because of these special relations, but you don't see those until higher level math classes, okay? But we're going to learn about it here, so if you do move on to take trig or pre-calculus, you'll get to use some of these facts about functions having these special things, okay? So there's another special thing with inverse functions, okay? So before I dive too deep in, I can actually take inverse functions and use what we did in section 1 and compose them, and something special will happen, okay? No matter which order you compose them in, I want you to notice this about these functions. So this was an example that we did on the last page. So if you take this and we do a composition, let's see if I have enough room for myself to fit in here. So the outside function is f, so it's 3 of blank minus 5. And we're sticking in the inverse function, which is x plus 5 over 3. Notice what happens. The 3 and the 3 cancel, right? And so, let's see. What am I left with? X plus 5 minus 5. What happens to the plus 5 and the minus 5? They go away. What are you left with? Just x. That's one of the really neat things with functions and inverse functions. When you compose them, everything will kind of kill itself off, and you'll be left with whatever you originally plugged in. You'll be left with just x, or if I did f of inverse of 3, you'll be left with a 3, or whatever you plug in there is left over. And you could do the same thing here. Maybe I'll do that. Let's see. The outside function this time is the inverse function, so blank plus 5 over 3. What are we plugging in? We're plugging in f of x, 3x minus 5. Well, what happens with the minus 5 and the plus 5? They add to 0. So you're left with 3x over 3. What happens to the 3's? They divide out to 1, so you're just left with x. So it doesn't matter whichever way you do these. If you do a composition of inverse functions, they kind of cancel everything out except for the x. That's a pretty neat relationship, right? Now, I got a little ahead of myself and excited earlier, telling you stuff that you'd use in trig and all that, these special facts and relationships between these functions. There's a special type of function called a one-to-one function, okay? A one-to-one function. What is a one-to-one function? Hopefully you can guess, since this whole section is on inverse functions, that it has something to do with the inverse function, okay? Here's the textbook definition, and then I will explain it. It says a function with where each x value, each x, corresponds to only one y value, and each y value also corresponds to only one x value. Okay, it's 1 to 1. This sounds almost like the definition of a function, and it's actually really close. It's just that we have this other piece. So a function, each x value is only related to one y value, right? A 1-to-1 function also means each y value is related to one x value. That means that the inverse is a function also. Okay, so it also is a function because you switch the x's and y's, and it's still, each input has only one output. Another way of thinking about this, if you want to go back to my example of the cheating men, we finally get to worry about the women cheating as well. To be a 1-to-1 function, we want nobody cheating. Okay? Men nor women. That's when we have 1-to-1. So the x's can't be cheaters, the y's can't be cheaters. If neither are cheaters, if neither are two-timing, then it's a 1-to-1 function. So for example, is this a 1-to-1 function? So let's see. If we check just to see if it's a function. So the x value of 1 is related to 4. It's hanging out with Mrs. 4. Do you see the x value of 1 hanging out with anybody else? No. The x value of 2 is in a relationship with the y value of 7. Do you see any other x values of 2? No. You may get confused and you look here and say, there's a 2 right there, but that's a y value. Okay? The x value of 8. Do you see any other x values of 8s? No. The x value of 0. Do you see any other x values of 0 matched up with somebody other than 9? No. So none of the x's are cheating. So there's no cheating x's, so it is a function. Now if you were to just check all the y values to see if any of the y values are cheating. Mrs. 4 is only dating Mr. 1. Mrs. 7 is only with Mr. 2. Mrs. 2 is only with Mr. 8. Mrs. 9 is only with... So there's no cheating men, so no cheating x's. No cheating x. There's also no cheating y. That means, yes, it's 1-to-1. Yes. 1, 2, 1. I forgot the other dash. 1-to-1. Okay. Now, you don't get to see how magically special 1-to-1 functions are. You kind of can, but not really too much in algebra. Once you expand out to higher level math classes, you get to see that this has some value to it. So just believe me on that. If you understand this when you do hit some things in trig or precalculus or calculus or even beyond that, this will have more importance to it, okay? More weight. Alright, now, I wanted to bring this to you. So remember we could do the vertical line test? Y'all remember that? We could say check a vertical line test to see if it's a function. We could do something similar to see if it's 1-to-1. We could do a horizontal line test. Okay? That's going to check to see if we have any cheating y values. So to see if something's 1-to-1, we need to make sure we have no cheating x values, vertical line test, and no cheating y values, horizontal line test. So let's see, are these functions 1-to-1? First off, this is a straight line. Can you draw a vertical line and cross it more than once? No, you cannot, so that means there are no cheating x's. So yes, it's a function. How about horizontally? Is there anywhere you can cross it horizontally and find a cheating y value? No, so this one is 1-to-1. Yes. 1-to-1. How about over here? No matter where you draw a horizontal line, the most you can cross it is 1. No matter where you draw a vertical line, the most you can cross it is 1. So there's no cheating y values, there's no cheating x values, so yes, this one's 1-to-1. And finally, let's do the last example here. Is it a function? Are there any cheating x values? I cannot find any cheating x values, because if I draw a vertical line, it can only cross it once. Are there any cheating y values? And the answer is yes. I can draw a horizontal line, and I can see that I have Mrs. 3 is hanging out with 2 x values. So this y value is cheating, so this one's not not one-to-one. Okay? So just like the vertical line test, we could do a horizontal line test. Okay? Alright, and that's all we have for you today, so be sure to try your worksheet. Okay? We're getting close to the end. These are our last few sections. We studied all these inverse functions today, and then we're going to dive into some special functions. Okay? Special functions that are functions in the inverses of them over the next few lessons. So y'all hang tight, we're going places. I'll see y'all later.